Hello and welcome to I Know Dino. I'm Garrett.
And I'm Sabrina.
And today, in our 392nd episode, we have a special edition by Sabrina all about what makes a dinosaur a dinosaur.
I don't want to give too much away, but there are a lot of different directions this could have gone.
Yes. And you also have Dinosaur of the Day, Erlikosaurus. And I've got a fun fact which kind of builds on your what makes a dinosaur a dinosaur. It's going to be about just how successful were dinosaurs.
Excellent.
But before we get into all of that, of course, we want to thank our patrons. And this week, the patrons we're shouting out to are Miriam, Pipiceratops, Vincentrosaurus, Chris, Polycanthus, Stefan, Eric, Jeff, Ashley the Acrocanthosaurus, and Ray.
Yay, thank you so much, everybody, for your support and for being our patron. And of course, we could not do this show without our dinosaur enthusiasts in our Patreon community. So, jumping right into it, what makes a dinosaur a dinosaur? And I am mostly going to be talking about non-avian dinosaurs, but you kind of can't help but talk about birds.
Yeah.
So I'll get into some bird stuff in a little bit.
Well, most of the distinction about dinosaurs is about the early dinosaurs. And then if you can figure out what those early ones are, then everything after that sort of falls into place.
Yes. So let's start with the fact that just because something has been fossilized, that doesn't mean it's a dinosaur. And I know a lot of our listeners already know this, but, we're starting at the basics here.
A lot of people don't know that. Like every time there's a new mammoth discovered, we get a text from somebody like, "Did you hear about this dinosaur?"
Yeah.
Like,
which it's
not
still
even close.
exciting news, but it's not a dinosaur.
It is not.
So just to list some other animals that are not dinosaurs, includes mosasaurs, ichthyosaurs, plesiosaurs, pterosaurs, Dimetrodon. That's a synapsid that went extinct about 40 million years before dinosaurs existed, and it's more closely related to humans than we are to dinosaurs. But it looks really dinosaur-y. Dinosaurs are also not lizards. Lizards are lepidosauromorphs. That's this group of reptiles with diapsids. It's a type of tetrapod that are more closely related to lizards than to archosaurs.
And archosaurs are mostly dinosaurs, but also include
crocodilians, birds, pterosaurs.
Yep.
Lizards also have a sprawling gait, as well as a sliding quote-unquote joint between the coracoid or shoulder and sternum, and they have pleurodont teeth. Their teeth are attached to the bony socket. For example, what you see the fangs of snakes.
Yeah, it's a bony socket as opposed to like a gummy socket like we have and dinosaurs have.
Yep. So let's get into some characteristics of dinosaurs. Now, dinosaurs, we know, they lived in the Mesozoic. That includes the Triassic, Jurassic, and Cretaceous periods. That was between about 245 to 66 million years ago.
The dinosaur piece of that, the Triassic, started a little bit earlier.
Yes. And non-avian dinosaurs, they lived for such a long time that the time between when Stegosaurus and T-Rex lived is actually longer than the time between when T-Rex lived and us today.
Yeah. Stegosaurus was already a fossil when T-Rex was walking around.
Yep, they never crossed paths.
Yeah. T-Rex might have tripped on some other dinosaur fossils.
Yeah.
Walking around.
Now, dinosaurs, they had a hole in their hip sockets, and that probably helped them position their legs underneath their bodies, so they didn't sprawl or splay, and that would have helped them better support their weight and made it more efficient to move around. It would have taken less energy to do that. And then they could use that energy that they saved in other ways, like helping with survival and reproduction. Some other features that non-avian dinosaurs had in common, these aren't necessarily dinosaur-specific, like other animals had these things, but dinosaurs definitely had them. Most of them lived on land. They constantly replaced their teeth. They were vertebrates. They had backbones. They had a hole between the eye socket and nostril, but all archosaurs have this, so also pterosaurs and crocodilians. These holes help to lighten the skull. It's actually a little bit hard to define what makes a dinosaur because the telltale features of what we used to say made a non-avian dinosaur, definitely a non-avian dinosaur, that list keeps shrinking. So one example is we used to say that they had 3 or more fused vertebrae in the sacrum, but Then you look at something like Herrerasaurus, and Herrerasaurus only had two.
Hmm.
So you can't say that anymore. Unless you decide that Herrerasaurus isn't a dinosaur, but that's a whole other conversation.
Yeah.
Another example is we used to look for a depression on the top of the skull where some jaw muscles attached. And then in 2017, a teleocrater was formally named and described by Sterling Nesbitt and others. And teleocrater is not a dinosaur, it's an archosaur, an Ave metatarsalian archosaur. It's in this group called Aphanosauria. That's the sister group of Ornithodira. And Ornithodira is the group that contains dinosaurs and pterosaurs. So it's closely related-ish. It's a reptile. It was about 6.5 feet or 2 meters long and slender. It lived in the middle Triassic, and it had this long neck and tail, and it walked on 4 legs. And it also had that depression on the top of its skull, which is what we used to say dinosaurs had, but this was not a dinosaur. Now, teleocrater, it looked pretty different from what paleontologists thought it would look like, based on, early dinosaurs being bipedal, for example, because it took them a long time to figure out what exactly teleocrater was. And teleocrater did have a faint dimple on its pelvic bone, but not a hole, tellingly, and that means that it's definitely not a non-avian dinosaur, because that's kind of the main feature we look for now, is that hole in the hip socket. When Richard Owen coined the term dinosauria, and dinosaur means terrible lizard in Greek, he mentioned that the original 3 dinosaurs, Megalosaurus, Iguanodon, and Hylaeosaurus, they all had features such as their legs being upright and under their bodies, and then he also said that they had 5 vertebrae fused at the sacrum. But that's just not enough for us anymore.
And that's often way too many fused vertebrae, too, because you were saying that Herrerasaurus goes all the way down to 2.
And there's a lot of dinosaurs with 3, and it's also just really hard to have this whole group. I mean, at the time, we didn't know just how diverse dinosaurs were, but to base it on just 3 types, it's hard to keep that up.
And legs being under their bodies isn't really a anatomical feature. It's sort of a description of an animal, which is more like a Linnaean sort of old school way of classifying an animal, not really a really useful modern way.
Yeah, and there's other features that are no longer considered distinct enough to tell if something is a dinosaur. So, just for some examples to give you context, we used to say an enlarged crest on the upper arm bone where the muscles attached was a feature. But you can see that feature in dinosaurs and dinosauromorphs such as Silosaurus. We also used to say there were bony projections at the back of the neck vertebrae, but you can see that in dinosaurs and dinosauromorphs such as Silosaurus and Asilosaurus. Dinosauromorphs in general, they're so similar to dinosaurs that there's been a lot of debate over whether or not some dinosauromorphs are in fact dinosaurs.
Yeah, that's just drawing the line between what makes the Dinosauria group Dinosauria versus what makes it just outside in Dinosauromorph. Because since it's evolution and evolution's messy, it's on a continuum, and it's pretty arbitrary where humans draw that line and say, like, you count as a dinosaur, but you don't.
Especially when you think about all these animals that were living at the same time in the Triassic, and they looked so similar.
Yep.
Just some examples, Altipus, we covered that one in episode 366, and Pisanosaurus, we covered that one in episode 354. Both of those had a lot of confusion and debate around whether or not they were a dinosaur.
Or just a dinosauromorph.
Exactly.
Shouldn't say just a dinosauromorph.
Yeah.
They're still their own genus and important animals.
Yes. Now, it's unclear why dinosaurs did so well after the end Triassic extinction event, but it's possible that they had certain characteristics to help them. Unfortunately, at this point, it's unknown what those characteristics are.
Yeah, because there isn't anything super obvious like, oh, look at that feature. Just having a different hole in the hip bone doesn't seem super important.
What did that do? Why did they thrive while all these other animals went extinct?
Yeah. Other animals that could still walk upright and had similar teeth or had, like all the different features seem to be in other animals.
So now I'll just mention a little bit about how we organize dinosaurs. When it comes to the dinosaur family tree, for over 100 years, dinosaurs were thought to be organized into 2 groups. You've got the ornithischians. Those are those bird hip dinosaurs with the backward oriented pubic bones.
And that's how modern birds are, which is why they're called ornithischians. They also have their pubic bone pointed backwards towards their little tail.
Yes. And then you've got the saurischians, which are those lizard hip dinosaurs with the forward oriented pubic bones.
Just like modern lizards. Thus the lizard hipped.
Yep. But then in 2017, Matthew Barron and others, and we interviewed Barron in episode 145 about this, proposed that dinosaurs should be organized into different groups, Ornithiscalida and Saurischia. And then in 2018, they revised it to Ornithiscalida and Sauropodomorpha.
Yep.
Now, Ornithiscalida includes ornithischians, and that's like ankylosaurs, stegosaurs, ceratopsians, hadrosaurs, and it also includes theropods. Not everyone has accepted this way of grouping dinosaurs, and then later studies even found that both ways of grouping dinosaurs, either the ornithischian saurischian way or the ornithiscalida and sauropodomorpha way, were almost just as likely that they were both correct.
Yeah, statistically, the computer's like, yeah, either way.
Either way could work.
Basically.
Although statistically, the original-ish one, the ornithischian and saurischian way, was just a little bit more likely.
It depended who was doing the scoring of the values, because when Matthew Barron does it, they come up as a little bit more likely to be Ornithiscalida. But when other people do it, they went back and forth on papers a couple times.
That's
I think
true.
you scored this dinosaur. And it ends up coming down to a few key features on some of the very earliest dinosaurs.
Which are the hardest to know about.
And a lot of them are really partial skeletons too. So it's like, does this little bump count as a real bump or not?
Oh, right. Or is it the way it fossilized?
Yeah.
Yeah. So there's still a lot to learn here. And that also makes it really hard to know what features make a dinosaur a dinosaur. So in general, it does help to have more descriptions and definitions of characters of fossils.
Yeah. And it's really reliant on how many dinosaurs we have from that middle to maybe even early Triassic time period. And if we find a really good one or a few more really good ones, it might be able to finally settle this.
Oh, yeah.
But
that'd be cool.
That does also point to why it's so important to define a dinosaur, because you have to know what you're including in this tree. And if you're including certain dinosaur morphs, it could screw up your analysis.
Yes.
And you might end up with Ornithiscalida when you shouldn't, or vice versa.
And then once you have these clear definitions, that could eventually help us figure out why were they so successful as a group. What we do know about dinosaurs, they did not drag their tails on the ground, and they were not sluggish animals, and they were not ectothermic. They didn't depend on the sun or other sources of heat to regulate their body temperature.
Yes, I think we know those things for sure. I'm pretty sure there are a few tail drag marks fossilized. It's been a while since I went back and looked at, how well accepted those are now. And then the ectothermic thing, yeah, we think they were like us and endothermic, meaning warm-blooded, but maybe the early ones, like the earliest ones, I don't know how confident we are in the very earliest ones.
I think at this point we're fairly confident. But that doesn't mean that a discovery happens down the road and upends all this.
Yeah.
So again, dinosaurs are archosaurs. That's a group that includes pterosaurs, crocodiles, birds. Dinosaurs have been found on all 7 continents. And as we talked about a little bit at the beginning, birds are avian dinosaurs.
And are still on all 7 continents.
Yes.
They were on all 7 continents and they still are.
It's pretty amazing. And Thomas Huxley first suggested that birds are dinosaurs back in 1868. This is not a new idea.
No. And people for a long time, even way before Huxley, have recognized that dinosaur tracks look like giant bird tracks.
Yes. Yeah, and there's even some different stories and myths around these tracks.
Yeah, like thousands of years old.
Some things that birds have in common with non-avian dinosaurs. They lay eggs, though modern birds lay 1 egg at a time, and then primitive birds and dinosaurs had 2 oviducts, like crocodiles, and they laid 2 eggs at a time, so it's a little bit different. Birds communicate with visual signals and sounds, and dinosaurs probably did too. You've got the horns, frills, crests, sails, feathers, all of that can be used for
A
communication.
lot of them do seem very showy for anything other than visual communication.
And then they may have also hissed or ground their jaws or clapped or splashed or beat their wings. On a side note, crocodiles and birds vocalize in different ways, so the ability to vocalize probably evolved independently, and maybe their common ancestor didn't make sounds. Might have
Oh,
been
interesting.
mute.
Huh. I think that some of that has to do with their size, though, because really big land birds like do that booming thing,
Mm-hmm.
and that's not that different than what crocodiles do.
Yeah, but so they might sound the same, but the way they do it is a little different.
Oh, gotcha.
Now, the color of Anchiornis, that's our dinosaur of the day in episode 389, that helps to show the importance of visual communication. Just going back to dinosaurs probably communicated visually in addition to sounds. Both birds and dinosaurs had wishbones. They look really similar as embryos.
Yeah. Well, not even just birds and dinosaurs, like almost all vertebrates look pretty similar in the earliest parts of our embryo.
That's
even
true.
humans. You look at a human embryo and you're like, is that a fish? What is that?
That's true. That's true. They also have feathers in common. You know, birds have feathers, and at least some dinosaurs had feathers. And they have scales in common because birds have scales on their feet.
Yep. And a lot of birds and dinosaurs both have pretty similar looking three-toed feet, which is why they have those similar tracks.
Mm-hmm. Or just look at a cassowary foot and you'll think, dinosaur.
Yeah. I think dinosaur even when I look at like a crow foot, like at the beginning of Jurassic World, but they're like zoomed in on a foot and you think it's a dinosaur foot and they zoom out and it's a crow.
Yeah.
That's one of my favorite parts of those movies.
Yeah, I liked that scene. There's a lot of things that the first birds had in common with many Coelurosaur dinosaurs. And Coelurosaurs, it's a subgroup of theropods and the closest relatives to birds. So it makes sense they've got things in common.
It includes T-Rex and dromaeosaurs and all sorts of popular theropods.
Compsognathids, ornithomimosaurs as well. So some things they had in common were they had long arms and forelimbs and claws.
Usually, T-Rex didn't.
Oh, yes. That's true, relatively. Anyway, they also had claws on the hands. They had large eye openings in the skull. They had a pubis that shifted to a more backward orientation, flexible wrists, hollow bones, a reduced but stiff tail, S-shaped necks, long foot bones, wishbones, and they had some similar egg microstructure.
There's a lot of similarities.
Mm-hmm. Now, obviously, birds changed a little bit because they don't look exactly, they're not even close to the same size as some dinosaurs. That's just one feature. So yeah, they tend to be smaller than their ancestors. They also had a more juvenile-like skull shape as adults. That's this thing called paedomorphosis, where you keep that ancestral juvenile trait as an adult. So like dinosaur juveniles had a different kind of skull shape, and now adult birds tend to have that skull shape. Over time, birds' faces got smaller and their eyes, brain, and beak grew. And in doing that, that might have helped birds shrink in size. Birds, we think, overall probably shrank fast, so being small could have been helpful or useful. While other dinosaurs were getting bigger, the ancestors to birds were getting smaller and actually shrinking something like 160 times faster. This might have helped birds with moving to trees, and trees are great for shelter and for finding food. It probably helped them with flight, too. And if you want to hear more on birds and dinosaurs and flight, check out our episode 390, where Garrett dove deep into that topic. And I'll talk more about similarities between birds and dinosaurs and beaks, but first, we're going to pause for a short ad break. All right, we're back. So, beaks also helped birds, as you can imagine. Birds can use their beaks to find food, to clean things, to build nests, and to care for their young. It's basically like their hands, if you think about it. We use our hands for all the same things. Modern birds, just in terms of how birds changed over time, they also have toothless beaks. Their forelimbs are longer than their hind limbs. They have pygostyles, those are those bony plates near the tails, as well as unfused shoulder bones, And then, of course, all birds have feathers.
Yeah. And that's true for some non-avian dinosaurs too.
Hmm.
Although not all birds, again, this is like in general, because you've got things like kiwis and other flightless birds that basically have tiny arms that are a lot smaller than their hind limbs. And I don't even know if a kiwi has a pygostyle. I guess it probably does. They got a pretty round body.
That's true, they do.
But there were some non-avian dinosaurs that had pygostyles as well.
Now, possibly the oldest bird was Archaeornithera. It's an extinct ornithuromorph, and that's the lineage that led to modern birds. And it's the oldest known one, the oldest one we know about so far, lived about 130 million years ago. It looked like a modern bird. It had long legs, a beak, a fan shaped tail, and flight feathers. And it was small, about 15 centimeters or 6 inches tall,
That is pretty small.
and modern bird like.
Although we should mention Archaeopteryx because the jury is still a little bit out on how that relates to modern birds, and that's significantly older than Archaeornithera.
Yes, well, I think this one's like the one we know about for sure being a bird, is the oldest known one.
Or, yeah, probably more likely than Archaeopteryx.
Just as a fun aside, another way that we kind of know birds or dinosaurs, look at Chickenosaurus, which we've talked about on our show, including episode 37, where we interviewed Jack Horner and talked about it.
Yeah, that's the idea that you could modify a chicken embryo to look like a dinosaur. It still wouldn't actually be a dinosaur or a non-avian dinosaur, but it would look like a non-avian dinosaur. And they got some of the pieces of the puzzle, like giving it a snout instead of a beak and giving it teeth. And I think they did something with the foot to make it more bird-like, but they haven't figured out how to give it a tail yet, like, instead of just a pygostyle.
Yeah, I think there was something about the sternum too, but they've made a lot of progress. Or again, as we mentioned before, you just look at a bird's foot. You think, yeah, that's a dinosaur. You can see the connection.
Oh, yeah. Just scale it up, and it's clearly the same track that you see for like a T-Rex footprint.
Mm-hmm. Now, how did dinosaurs compare with other archosaurs? Well, pterosaurs and dinosaurs are different from crocodiles based on how their ankle bones are arranged. But dinosaurs and pterosaurs separated around 250 million years ago. And again, dinosaurs have the hole in the hip socket. They also have a long crest on their upper arm bone. Crocodiles, however, haven't changed much in 247 million years because they didn't have to. They're already really well suited to adapting to changes in their environment.
I think their heads did get a lot flatter, though. That was one thing that changed.
Could be.
But you're right. Compared to the difference between an early dinosaur and a bird,
Mm-hmm.
there's not
It's
much
not
change.
that different.
with crocodiles.
There's at least 18 extant or living crocodile species today. Some earlier crocodile species were more specialized and then went extinct when their environment changed, so maybe they were too specialized. And one example of that is apparently at one point in time there were vegan crocodiles.
I don't know about calling them vegans because we know that animals will eat meat if
True.
it's available.
True.
But herbivorous, sure.
Which also seems odd for a crocodile.
Yes.
A study in 2021 by Maximilian Stockdale Michael Benton found that the environment affected crocodile evolution. Crocodiles tended to evolve more quickly in warmer environments, which worked well after the asteroid hit that killed the non-avian dinosaurs. There was some time after where the temperatures rose drastically.
Interesting.
Yeah, so some features that work really well for crocodiles is that they get warm from the sun. They don't make their own body heat. They don't need to eat that often. They can fast for months in some cases.
That's got to be a huge advantage during a mass extinction type event when
Yes.
the ecosystem is totally screwed up.
Exactly.
I think they're also really good at scavenging. There's a lot of crocodiles that spend a bunch of time being carnivores and then like a different season being scavengers, which would be really helpful.
Oh, yeah. Yeah, very adaptable. They can also hold their breath a long time. And like you said, scavengers, but they'll also eat, anything, fish, live animals, whatever they can get their jaws on. And they can survive terrible injuries. So because of all these factors, they can live in a lot of environments, rivers, swamps, open ocean, etc.
Yeah, they are really spread out. For my fun fact, I was looking at how spread out these different groups are that are closely related to dinosaurs. And for I think I came up with a low 20s number of species, but still, for such a small number of species, they are very spread out all over the earth.
Oh, yeah.
Not as much as dinosaurs, but still pretty impressively
Still
spread
pretty
out
good, yeah.
for such a small group.
Plus, they survived the asteroid.
Yeah.
Our crocodilian ancestors may have had more active metabolisms, though, than we previously thought. There's this study in 2019 by Jorge Kubo and Noor Eddin Halil. And just some background. There's endotherms. We talked about the warm-blooded, though, it's not quite that simple, but basically warm-blooded animals like mammals and birds that generate their own heat internally. And then you've got ectotherms, which are cold-blooded, like reptiles and amphibians, and they get their heat from their environment.
Yeah. Sometimes, and the body temperatures aren't that far off. It's usually like a few degrees Celsius. It's just that the ectotherms have to bask in the sun to get their heat and all that kind of stuff, like you're saying, getting it from the environment.
Mm-hmm.
At least mostly, while endotherms, yeah, we just produce it internally. So
Yeah, so we can move around however we please.
And on average, we're warmer.
Yeah.
That's why we call warm-blooded and cold-blooded for short.
Now, alligator embryos, they develop this unique opening before they hatch, and that allows blood to bypass the lung, and that basically turns their endothermic heart to an ectothermic heart.
What?
Yeah. So it could be that ancestral crocodiliforms were endothermic or warm-blooded.
Weird.
Crocodiles have a lot of interesting things going on.
Yeah.
In 2016, Kubo studied an Azindosaurus specimen. That's an old Archosaur relative that lived in the Triassic, and the skull was once thought mistakenly to belong to a dinosaur, as a lot of things are that lived in the Triassic.
Yep.
They did histology, they looked at slices of the bone, and they found that its resting metabolism was most likely much higher than most modern ectotherms and similar to modern living mammals and birds. That could mean that Archosaur relatives in the late Triassic were endotherms, which could mean that early crocodiliforms had higher metabolic rates and were more endothermic than ectothermic, and they could have moved very quickly on land. So maybe they were warm-blooded, though there is some debate, and there's debate also, like Garrett mentioned, around cold and warm-blooded, kind of being on a spectrum. It's not in fixed categories. Now, the climate was warmer in the late Triassic and early Jurassic, and that could have led to the higher metabolism. And during the Mesozoic, a lot of crocodilians went back to the water, and they transitioned from land animals to semi-aquatic and ambushing their prey in the water. And that may be why they evolved to have a much more ectothermic lifestyle.
Yeah. Yeah, because water, you get a more consistent temperature. And if you're competing with fish and dealing with that whole environment, maybe it's more beneficial.
Yes. So now we've established birds are dinosaurs. Not crocodiles or pterosaurs, but birds are dinosaurs. We know of over 1,000 non-avian types of dinosaurs, and there's over 10,000 species of birds. So there's a lot of diversity in this group.
Yeah. Yeah, so we've found specifically over 1,000 individual species of non-avian dinosaurs just from fossils.
Mm-hmm.
So that's probably a pretty small fraction, I would guess.
Yeah.
Some people estimate that there were only like 3,000 or 4,000 that we'll ever find. But considering there are 10,000 species of birds today,
yeah,
just like at this moment in time,
seems likely that there were more types of non-avian dinosaurs as well.
Exactly.
Now, some of these dinosaurs, they swam, some flew or glided, some were big, over 100 feet or 30 meters long. Others were small, about 2.5 feet or 0.7 meters long.
If you include the bee hummingbird, they get real tiny, just a couple grams.
That's true. I was talking about the non-avian dinosaurs, but if you get into birds, they get much smaller.
Well, yeah, there was even that bird/dinosaur. Yeah, I guess that's the thing. When you're talking about non-avian dinosaurs, the smallest dinosaurs are avian.
Mm-hmm.
So then you got to make that distinction too.
Now, some dinosaurs had feathers, others had scales, some had crests, others had armor, some had long necks, others had sickle claws, some were herbivores, others were carnivores, some walked on 4 legs, others on 2. So just a wide variety of features.
Mm-hmm. And some started on 4 legs and switched to 2, or Started on 2 legs and switched to 4.
Hmm.
Or somewhere on 2 the whole time or 4 the whole time.
But as a recap, when it comes to what makes a dinosaur, it's all about that hole in the hip socket. That's the main feature we're looking for these days.
The open acetabulum.
Exactly. And now onto our dinosaur of the day, Erlikosaurus. It was a Therizinosaurid that lived in the Late Cretaceous in what is now Mongolia, found in the Bayan Shireh Formation. And we're talking about it today because it appears in Jurassic World the game and in Jurassic World Alive. And as we know, Jurassic World Dominion is coming up out in a few weeks. And in those games, it has fur-like feathers, which is cool because its body probably was covered in feathers. Erlikosaurus also had a bulky body with a small head, large claws, and long tail.
Much like other therizinosaurs. And, I mean, you said it has a small head. I guess it depends what you're comparing it to, because they sort of had a long, horsey head. That's how I think of them, at least. Almost like an anteater in a way. Sort of like elongated head. Definitely bigger proportionally than something like a sauropod.
Right, but for a therizinosaur, it was kind of small.
Okay.
Now, the reason we think its body was probably covered in feathers is based on preserved feather impressions found on other therizinosaurs, Beipiaosaurus and Jianchangosaurus. Erlikosaurus is estimated to have been 11 feet or 3.4 meters long and weigh between 330 to 550 pounds or 150 to 250 kilograms.
That's so heavy for that length.
Yeah.
I'm so used to dinosaurs that are 11 feet long, weighing
And light.
like 40 pounds or something, maybe a couple 100 pounds. But yeah, almost a quarter ton there. That's like,
Therizinosaurs were weird.
I mean, they had such short tails that that's a lot of mass in between the front and end compared to things that have a really long neck and a long tail.
Okay, compared to other dinosaurs, it had a short tail. But compared to other animals, it was still kind of a long tail.
Yeah. I guess.
All right, we disagree there. Erlikosaurus had a large humerus, about 12 inches or 30 centimeters long. It had strong arms with long claws.
Oh, yeah, extremely long claws.
Yep. It had a backwards directed pelvis. It also had claws on its feet, possibly for self-defense. It had 4 toes on each foot.
Yeah, and its backwards directed pelvis is really weird because it's a theropod, and theropods usually have the forward face because they're saurischians, right? They're supposed to have the lizard hips with the forward facing pubis, but no, it goes the other way.
Again, therizinosaurs are a strange group.
And one of the theories on that is that they had big guts to digest the plants, so then that hip ended up rotating the other direction.
Yes, exactly. Another thing that makes it kind of weird, this herbivorous theropod. Now, Erlikosaurus had claws on its feet, possibly for self-defense, and it had 4 toes in each foot.
That's funny to say that it had claws on its feet for self-defense when it had huge claws on its hands.
Yeah.
Like, does it really need to involve the feet when it's got such massive claws on its hands?
Well, that's why it's possibly for self-defense.
Well, it does have 4 toes, which is super weird again for a theropod. So maybe it got an extra toe because it was kicking stuff all the time and that extra claw helped.
Could be.
I don't know. It's just random speculation.
It also had a somewhat long snout and a somewhat long brain. And it had this enlarged forebrain, which might have helped it with evading predators and helped it with being more social. Its olfactory tract was much larger than the brain, so it had a pretty good sense of smell and good hearing. It also had good balance. Erlikosaurus fossils were found in 1972 during a Soviet Mongolian expedition, and they included a well-preserved skull, a nearly complete right foot, and a nearly complete left humerus. Other fossils were found too, including fragmentary cervical vertebrae.
Also known as neck vertebrae.
Erlikosaurus was described in 1980 by Pearl and Barsbold, and the type species is Erlikosaurus andrewsi. The genus name means Erlich's lizard.
Yep.
And it refers to Erlich, quote, the Lamaist deity, king of the dead, end quote.
Wow. That's quite a title.
Yeah. And the species name, andrewsi, is in honor of Roy Chapman Andrews. Erlikosaurus is the second therizinosaur found in the Bayan Shireh Formation. And they found a very complete skull. The skull's been described as, quote unquote, remarkably uncrushed.
Remarkably uncrushed.
Yes.
I guess that's a problem with Therizinosaur skulls then.
That's a problem with skulls in general. The holotype skull is about 10 inches or 25 centimeters long. Then it was interesting. In 1981, a year after Erlikosaurus was named, Pearl named and described Erlikosaurus again as if it hadn't been done already, but he spelled it a little bit differently. He spelled it with a C instead of with a K. So most scientists consider Erlikosaurus with a K to be the valid spelling, since that was the first spelling.
Yeah, that's all I've ever seen. That's super weird.
Mm-hmm. Erlikosaurus was the first therizinosaur, and back in 1980, when it was named, therizinosaurs were called segnosaurs, and it was the first one where a complete skull was found, and that helped paleontologists learn a lot more about this group. So, back in the 1970s, early 1980s, segnosaurs, now therizinosaurs, were thought to not be dinosaurs because they're very strange.
Yeah. Like why would it have 4 toes and the hips going the other way, but also be an herbivore and all this kind of stuff?
Yeah. But then, in 1970, Rojdestvensky suggested they were theropods. And in 1980, therizinosaurs were thought to be slow and semi-aquatic.
Huh.
But then more therizinosaurs were found, and they were seen to be more theropod-like. James Clark and others in 1994 redescribed the Erlikosaurus skull and found the features to be consistent with the idea that therizinosaurs were theropods as well. In 2010, Gregory Paul suggested that Erlikosaurus was synonymous with Enigmasaurus, and Enigmasaurus was named in 1983. They were found in the same formation, and only pelvic fossils were found for Enigmasaurus, but no pelvis has been found for Erlikosaurus.
So you can't compare them.
Yes, so not everybody agrees with this.
Enigmasaurus is a cool name, and it actually sounds kind of like Erlikosaurus.
A little bit, yeah. The two species were also found in different parts of the formation, the upper and lower boundary. And the hip of Enigmasaurus looked very different from a close relative to Erlikosaurus, Segnosaurus. So that's another reason why not everybody agrees. As we mentioned, Erlikosaurus was herbivorous and had this large gut to process food. It also had a well-developed keratinous beak and teeth in its jaws, and it could crop plants and strip leaves off of branches. A study in 2013 by Stefan Lautenschlager and others CT scanned the skull of Erlikosaurus and found that the beak helped stabilize its skull while it was eating, which would have made the skull less likely to bend or get deformed. Before this study, beaks were thought to have replaced teeth to make the head lighter and eventually help with flight, just in general, not Erlikosaurus specifically.
That's not a great way to look at evolution because we knew beaks evolved on animals that didn't look like they could fly at all. And there isn't this sort of preference towards the final form. Like you can't post hoc rationalize why something evolved something. Like it knew its great whatever
Yes.
descendant was going to want to fly. So it evolved this beak, which would be useful in this way later form.
Right.
Like, so that's not how it works.
No, and in this case, beaks can be used for other purposes, like helping with eating.
Yep.
A 2021 study by Fionn Weissema and others digitally modeled and simulated over 40 theropod jaws from 5 groups that included Tyrannosaurus, Velociraptor, also Ornithomimosaurs, Therizinosaurs, and Oviraptorosaurs. And they found that theropods evolved to have more structurally stronger jaws to eat tougher food. The jaws, they would get more stable when they're biting, and then they were less likely to have bone fractures.
Or dislocations because they have that joint in their jaw too. So that's also helpful.
Yeah. And they found that the jaws became stronger in both carnivores and herbivores. In theropods, yeah. And Erlikosaurus had downward bending jaws that could help relieve stress when cropping plants. It did, however, have a relatively weak bite force compared to other theropods, which maybe you'd expect it being herbivorous and all.
Yeah, because the plants don't struggle while you're biting them.
Yeah, exactly. In 2012, Stephen Lautenschlager found that Erlikosaurus, the bite force, was low compared to other theropods and in relation to its body mass. However, Komodo dragons tend to have weak bite forces for their size. Having the keratinous beak, though, for Erlikosaurus, that would have been an advantage because it's always growing, so it could quickly repair fractures.
Interesting. Never thought of that as an advantage of a beak before.
Yeah, me either. Then a 2015 study by Stephen Lautenschlager and others digitally modeled and analyzed muscle strain for 3 theropods when they were opening their jaws. They looked at Erlikosaurus, Allosaurus, and Tyrannosaurus, and they also compared them to crocodiles and birds. And the muscles that open and close jaws, they can only stretch so much before tearing, and that plays a role into what an animal can eat. Allosaurus and Tyrannosaurus, they found could open up to 90 degrees, while Erlikosaurus was only about 45 degrees.
Oh, that's not that much.
No. And modern carnivores usually can open their jaws wider than herbivores. Erlikosaurus lived alongside another therizinosaur, Segnosaurus, but they probably filled their own niches. Erlikosaurus was much smaller than Segnosaurus. Segnosaurus was about 20 to 23 feet or 6 to 7 meters long, versus Erlikosaurus, which was around 11 feet, 3.4 meters long.
It's about half.
Yeah.
And then much less than half if you did it by weight, I'm sure.
Yeah. Segnosaurus also had different teeth from Erlikosaurus. Erlikosaurus had symmetrical teeth, and Segnosaurus had these complex features with serrations and cutting edges and could probably eat tougher vegetation. Erlikosaurus, again, it probably used its beak and then the muscles in its neck to crop plants, and it probably processed all that food in its gut. Whereas Segnosaurus probably processed its food more with its jaws and teeth.
Yeah, that's how we always imagine it, because that's how we do it.
Mm-hmm.
But when you have a gizzard full of rocks, you can just swallow the food in large chunks and chew it once it gets in your stomach, basically. At least some of them could.
I don't think there's been gastroliths found with any Erlikosaurus specimens.
But they're ancestors, some of them.
Now, Erlikosaurus lived in a semi-arid climate with lakes and rivers, and other animals that lived around the same time and place, in addition to Segnosaurus, included tyrannosaurs, ceratopsians, hadrosaurs, ornithomimosaurs, troodontids, pterosaurs, and fish.
And our fun fact of the day is that, put simply, dinosaurs are the most successful terrestrial vertebrates of all time.
Yeah?
And I think I can back that up. So this is not only because of how they cover the whole planet, how they did during the Mesozoic, and also how they do today, even more so with Antarctica, where you mentioned earlier how they were on all 7 continents. But also based on how much time from the history of vertebrates walking on land, dinosaurs have been a major component of that. So based on fossil evidence, the first terrestrial animals evolved about 375 million years ago. That's when Tiktaalik was alive, for example. It might have been a little bit earlier, but these were really more like fish that could prop themselves up on modified fins. They weren't going for a stroll for miles on land, which I think is really what you need to be considered terrestrial. You got to be able to walk around on land quite a bit, not just prop yourself up or even, like a seal flop around on the land a little bit. That doesn't really make you terrestrial.
Yeah.
The first fossils that seem like they could walk on land reasonably well were animals like pedipes, which means Peter's foot, that evolved about 348 million years ago. And it looks a lot like an amphibian, but it has arms and legs, and they actually have feet rather than flippers. So it probably was a pretty capable walker. Now, that was sort of where we were until a few months ago. And then there was a new method of estimating the earliest land vertebrates, which looked at body temperature of modern tetrapods. And this was a study by Matthew Morera and others in Evolution Letters. And they were looking at all terrestrial tetrapods. And by terrestrial tetrapods, this is basically everything that isn't a bug that walks on land. So the earliest land vertebrates are terrestrial tetrapods, and it also includes all living terrestrial vertebrates. Today, that group includes mammals, crocodilians, birds, also known as dinosaurs, turtles, lizards, and amphibians. And when I say lizards, I mean lepidosaurs. You were talking a little bit about them earlier. Basically, again, everything on land that you think of as an animal. It doesn't include bugs, which are technically terrestrial, but they're invertebrates, and that's a whole different ball game.
Right.
So it turns out that body temperatures evolve really slowly over time. And it makes a lot of sense because the cells in our bodies, for example, in human bodies, need to operate at a very specific temperature. They don't function like if you get a fever and you go above 104 degrees Fahrenheit, which is 40 degrees Celsius, things go very wrong.
Yep. They
You,
also go wrong if we get too cold.
yeah, hypothermia kicks in if your body temperature falls below about 95 Fahrenheit or 35 C, which means the entire range that we're really even remotely healthy is only 5 degrees Celsius or about 9 degrees Fahrenheit. And really, you can't spend much time at those limits either. It's like it's a narrow range. And all the cells in our body really rely on that. Proteins start degrading and failing, and you start freezing and having all sorts of problems if you go outside of that range. Because of that, because like our whole body requires that, it's hard to evolve a different temperature because all the cells that have different functions and use different chemicals and stuff have to be able to adapt to that new temperature. And there usually isn't a lot of evolutionary pressure to change that,
Hmm.
especially if you're an endotherm or a warm blooded animal, because you can regulate your own body temperature. So it becomes more a question of regulating that temperature effectively and maybe growing more hair if it's a cold place or less hair if you're in a warm place or things like that. A lot easier to do than all of your cells adapting to a new stable temperature. So, even though in endotherms our body temperature evolves really slowly, it also evolves pretty slowly in ectotherms, cold blooded things. They also rely on a pretty not as narrow of a range as endotherms rely on because they have to be able to deal with more changes in weather. But in order to function, they have to be at a pretty specific body temperature, which doesn't usually change much, but it does change over evolutionary time periods. So, what these researchers did is they basically looked at all the body temperatures of all the animals we could find, both living and extinct, and sort of map them all out and then try to trace back the trajectories of those body temperatures to a single point.
That sounds like a lot of work.
It's really cool. So they've got the mammals, the crocodilians, the birds, the turtles, the lizards, and amphibians all in their separate little groups in a nice little family tree looking thing, and then drawing them back to a single point. And basically, it looks like when you line up the lines of those evolutionary lineages, it looks like they converge at a point about 350 million years ago,
Hmm.
which is the same as that estimate some of those oldest terrestrial tetrapods that we found. So that seems to verify about 350 million years ago for the most recent common ancestor of all these modern terrestrial vertebrates or tetrapods. They're the same thing in this case. As a side fun fact, these researchers also found that nocturnal species have lower body temperatures than their close relatives who are awake in the daytime.
Interesting.
Yeah, it's super weird. So it makes sense for ectotherms or cold-blooded animals because when it's dark out, you don't have the sun to bask in, so you'd have to deal with lower temperatures. But it's also true for endotherms, warm-blooded animals like birds and
Hmm.
mammals. Super weird.
That is weird.
Also, in order of warmest to coolest, birds are the warmest warm-blooded animals. Mammals are next. Then you get lizards, crocodilians, turtles, and finally amphibians are the coolest.
Temperature wise.
Yes. Although that was interesting earlier, you're talking about how crocodilians used to be warmer.
Hmm.
Maybe they used to be warmer than lizards. I'm not sure.
That'd be weird.
So now, going back, now that we've established that the earliest terrestrial tetrapods were about 350 million years ago, and that's when us backbone havers started joining the giant bugs on land. Although we didn't immediately take over, there were still huge bugs on land for like another 50 million years.
Hmm.
Conservatively, we can say that non avian dinosaurs were around for at least 167 million years. That would be about 233 to 66 million years ago. But it's possible that that range might go up to 180 million years if there are some earlier undiscovered fossils out there. And depending on, like you were saying, what makes a dinosaur a dinosaur.
Hmm.
If some of these dinosaur morphs, like Niosasaurus or something, turns out to be a dinosaur, that pushes it back like another 7 million years right there. Just one single dinosaur defining it as a dinosaur rather than a dinosaur morph stretches it out. This means that non-avian dinosaurs were a major part of the ecosystem on Earth, on terrestrial Earth, for about half of the history of terrestrial vertebrates.
Oh, wow.
If you,
Very successful.
yeah, if you include birds rather than just non-avian dinosaurs, then dinosaurs have been a major part of land vertebrates for at least 2/3 of terrestrial vertebrate history.
That is impressive.
And I do mean like a major part,
Hmm.
because you mentioned that there are over 1,000 species of named dinosaurs, and we know that they dominated most of the ecosystems in the Jurassic and Cretaceous. Not so much Triassic, but they were doing okay for themselves. And then now there are 10,000 species of birds, so they're obviously very diverse and distributed. And there are ecosystems where birds are the apex predators. So in addition to time being 2/3 of vertebrate history, being, significant pieces of the ecosystem, we also have in number of species, they're a very significant portion, not even ending with non-avian dinosaurs up to the present day. And there are actually about twice as many dinosaur species at 10,000 as there are mammal species at 5,400. Another way to put that, which I've seen a few times elsewhere, is that the age of dinosaurs really isn't over because
They're
there's
still very much around.
there's so many birds everywhere and they do great. They're one of the most effective animals at living alongside humans too, which is pretty advantageous these days. Although mammals are often the apex predators, but not always. Now, I should say, though, lizards or lepidosaurs have dinosaurs slightly beat at about 11,000 species. Although dinosaurs are more widespread, they cover more ground with their 10,000 species than lepidosaurs do with their 11,000 species. Feathers, I think, really make a big difference there.
Hmm.
There are 8,000 species of amphibians. That's the next largest group in the terrestrial tetrapods. Almost 90% of those are frogs.
What? I didn't know there were that many types of
It's
frogs.
an insane number of frogs. It's like 7,000 species of frogs. It's ridiculous. I think a lot of those are in rainforests, like lots and lots of
Okay.
little frogs in rainforests, things like that. There are only 300 species of turtles, which is actually more than I knew about.
Yeah.
A lot of those are like river turtles and stuff. There really aren't very many sea turtles. And the lowest on the totem pole in terms of number of species is crocodiles at only 24 species. But as you mentioned before, even just with about 20 species, they do get around most of the planet. So, long story short, I think that dinosaurs are the most successful terrestrial vertebrates of all time, largely because they dominated most of the Mesozoic, which was such a long time period. But then, even after the Mesozoic, they're still doing great as birds. So, yeah, we've got a long way to go before mammals can be considered as successful as dinosaurs.
Yeah, I don't know if mammals will get there.
So we got to
Because
not wipe ourselves out for another 200 million years.
well, also the fact that birds are still around,
Yeah.
I don't see them going away anytime soon.
Well, mammals were still around when there were dinosaurs too. We were there in the Mesozoic.
Oh, true. We're there in the background.
Yeah. There were some big mammals here and there that were holding their own. Although I don't think mammals in the Mesozoic were as successful as birds are now.
Yeah, maybe not. And on that fun note, that wraps up this episode of I Know Dino. Thank you for listening. We started doing episodes like this because our listeners and our patrons requested it. So if you are not yet a patron, then go to our page at patreon.com/iknowdino. Thanks again, and until next time.